Hi, welcome to the Calculus 3 lecture series. And we are in the unit, the vector calculus. And this is our lecture number 7. We talk about the curl and the divergences. This is the video number 3 for these lectures here. So for the video number 1, we talk the basic definition of the curl and the divergences, and also we kind of watch a couple videos and give you a visual presentation about what is curl and divergences. Then for the video number 2 here, we did we were working on the formula for the curl and the divergences. It's kind of very mechanical type of the video. We show you how to use the formula, how to, to apply the formula to the problems here. Okay, so the last video we're going to talk about, we're going to go back to the Green's theory we discussed in the previous lectures. And we're going to see how do we put the Green series for the vector form by using the curls here. Okay, so now let's go to our lecture notes. And so we can start to work on that. All right, so before we start, okay, so before we start, let's kind of do a very brief review about the Green series we did. So we say the Green series is a smooth, simple curves, right? So we say C is a smooth, closed, simple, a simple curve, and rotate and with a what? With a positive orientations, right? Okay. So also we say that my vector field, the f of xy is equal to, I have the pxy to the r plus qxy to the j's here. So from the previous, so we know the way we define the Green series here, we say, hey, the Green series here, we say, okay, so basically it's like if you do the C here, right? So we said that this is the F dot the dr, all right? Then we say you can really change to is the closed curve, the region bounded by this closed curve is the D's, right? Then you can do the rho Q, rho X minus rho P, rho Y. Then you integrate, respective to this region. So that's why we say the dAs here. So now what is the next things we want to talk about? We want to talk about is how do I write the Green series into the, the vector forms here, right? So now think about it here. So now we have this vector form in the XYZ in the R3. So we can kind of say, okay, we can change these forms here. We can say here, you can have the, okay, so we can put it like this way. So we say, okay, so this is R2, right? So we can say we have like the P, X, Y, Z to the I plus Q, X, Y, Z to the J, because it's R2, right? So so I don't have like what the K components, right? So I say 0 Ks here, okay? Then we can say, okay, now for this functions here, of course here the pxyz, because I don't have z, so it stays a function of xy's, right? Then I will use the curl of the f, okay? So the definition about the curl of the f is here for the what? For the f of xyz here, okay? So now we say here, we know the way we said here, because this is the case, right? So we know the k dot product k is equal to what? Equal to 1. And also the rho p, rho z, because we are in the R2, right? So this one's here. So right now we are looking for this function, the curls here. So if I color coding that, maybe it's better. Then rho p, rho z, this will be equal to 0 because I don't have the z value. The same way is here, rho q, rho z is equal to what? Is equal to 0 here, right? So now if you plug into, so you plug into the curl functions here. So we know you can calculate that. So the curl of the f, okay, dot product, the k will just be what? Will just be the rho q, rho x minus rho p, rho y. So I'm not going to, go over the calculation. So basically you can find the curl and then dot product case here. So the first forms here, so this is, we say this is the line integral of the f of the dr, right? So that's what we have here, f of the dr. So then you can say here, you can say just like we do the green series, we can say it's the d rho q rho x minus rho p rho y, and this is the dAs here, right? And then the same ways here, right? So you can say these ones here, I can use the curls definitions here. So you will see here, this is the D, and then this is the curl F dot, right? So the K to the dAs here. So this form, we said this is the, so this is the, you can use the curl. So this is the first form. This is the vector form, right? So this is, we call it, this is the vector form of the green series. Okay. And also, like in here, I want to separate these ones here. So these ones here we call is line integrals, right? So the really these ones here, this is we call this is the line integral. Kind of get a little bit details here. So this is the line integral, okay, of the tangential components of f along the C's here. So that's what from our previous definitions, right? So we said this integrations here along the FDR is tangential components of the f of the C's here, right? And so basically, then when you change to these forms here, let's say we talk about this is our, the vector forms, right? So you can say is here is a tangential of the f along the C's, right? So it will be, so it's the double. So after you change it to the curl, so we say this is the double integral of the vector components of the vertical components. And that's why we say it's the k directions, right? So it's the vertical components is of curl over the region, okay? Okay, so that's what we say here. So that means the line integrals here. So this is a line integral we learned start from this unit. This line integral we call it the tangential components of the f's here. So you can look at this is kind of it's the double integral of the vertical components of the the curl. So you can treat this, right? So the now over the region D here. Now we're going to introduce another ones here. So this is the first form. Then another form of the green series, we call this the line integral. So here, if I have the C, still is a closed simple curves here. Then the f here, dot n, all right, and the ds. Okay, so these ones here, we can rewrite it, will be the double integral of the divergence of the f of xy dAs here. This form, okay, so this one we have not talked about it, and we're going to talk about this. This is we call the, this is the line integral, okay, of the normal components of f along the C. Okay, so what is that one is? Okay, so this is the normal components, right? So that means it is the what? Is the double integral. So it's the double integral of the divergences here of f over the region D. Okay, so far what we learned is the tangentials, right? So we have not learned the normal, the normal components, right? So these components here, that's why we call this is the, okay, so this is, we call this the normal components here, all right? So this one we call this the normal components. So it's a double integral of the divergences here. And then these things here, so this is here we have not learned. We're going to learn in the next, the one section after next sections here. So this is what we call this the flux. Okay, so this is the definition of the flux, and we are going to learn that in our next, in the next our the sections there. Okay, so that's it. Let's take a look at the summary here. So let's highlight what we learned here, right? So we said, suppose, okay, suppose C is a smooth, simple, closed curve in a plane. For the two dimensionals here, we can really think about the two dimensional. You can change that into a three dimensional with the, you don't have the Z, right? So now we can use the curl and the divergence operation to find the two vector forms, right? So the first vector form is the one we call the line integral. So it will be the curl f dot x dot k to the dA. So these forms here, so right now we are kind of distinguished this a little bit more detail. This is the line integral. We call this the tangential components of the f's here. Okay, so the same ways here, you can write the green series in this forms here. All right. So this form is C to the dot n ds here. This is, you can use equal to the double integral of the divergence of f of xy. And this is, we call this normal components of the f of x. And in general, we call the, so the terms of the, so the terms of this one is, we call this the flux, right? And we will take a look at more detail in the next sections here. Okay, so now let's take a look at some examples here. So let's say if f of x, y, z is equal to the 2xy and 4x plus 3y to the j, D is the triangle bounded by x equal to 0, y equal to 2, and y equal to 2x. And C be the boundary of the D. So let's use the vector form to the theory to find. Okay, so let's take a look here. So first here, let's do this, right? So the x equal to 0, y equal to 2, and y equal to the 2x here. Y equal to the 2x, so x equal to 1, y equal to 2. Okay, so this is the, the region we bound. And now I'm going to find the, so this is the C's, right? And so use the vector form to find the green series. So the first ones here, we want to find the tangential ones here. All right, so now let's take a look. So that we said the curl F here, dot K. So basically just like we shows here is rho Q, rho X minus rho P, rho Y here, right? So rho Q, rho X minus rho P, rho Y, you will get is 4 minus what? 4 minus 2X here. So that's why we can say, okay, this one's here is will be equal to, you do the double integral and you have a curl F dot K to the dAs here, right? So basically you just have the double integrals here, curl, we just find this one, the 2x, 4 minus 2x dAs here, right? So now you're looking for the bound. So this is 4 minus 2x. You can integrate the dy dx or dx dy. So if I integrate the dy dx, so the same as the dy, you go the y directions, right? So this is 2x over 2, and then x from 0 to 1. So you carry out this simple double integration, and you will get your answers here. So 10 over 3 here, okay? So now here, how about if I want to find, if I want to find, the line integral over what? Over the normals, right? So we want to find the line integral over the normal components here. So first things, let's find the divergence of the F. Divergence of the F is just the rho P, rho X, rho Q, rho Y, right? So rho P, rho X, so rho P, rho X is equal to what? It's 2Y. Then rho Q, rho Y, what is here? Will be 3, right? So I know my divergence will be 2Y plus 3. So then based on the previous formula, we know the line integral over the normal components is the double integration of the region of your divergence. So it's a 2y plus 3 over the region I'm trying to do. So this one's here, you can do the same way, just like we did before. This is a 2y plus 3. You can do the dy dx first or dx dy. So let's do dy dx. So I have a 2x to the 2, then x from the 0, 1 here. So it is the same, right? So you kind of, it's easy to do this double integration. So after you carry out this double integration, so it will be 17 over 3 here. Okay, so that's it. Okay, so for the, for this video, basically we are talking about, how to change the green series, into a vector type of the form by using the curl. So we know the curl is defined in R3, so you can, that's the key things here. You just set the K components equal, it's zeros, right? So you don't have the Z values here. Then those two formulas are very useful, right? So we're already kind of familiar with the tangentials ones here, the line integral of F. Then these formulas here is kind of the paved road when we go to the next topic when we talk about the flux, right? So we say these formulas here, this is what we call this flux. So we're going to do a detail, talk about what is a flux, and then we're going to have some very good theory also. All right, that's it. Okay, so that's it for this lecture series, the curl and the divergence. It's like it's kind of like it's a big topic. So that's why I divided into 3 videos, and I hope that this help you some. All right, that's it. Have a nice day, and looking forward to talk about the next topic about the vector calculus here. Okay, bye.